Good afternoon, everybody, and welcome back to Discrete Math. Plan for today is we're going to have some presentations on the Advanced Solutions 2 packet. We're going to go for a walk, apparently, and we're going to start our last major unit of the semester, which is graph theory. This time our packet even has a picture in it with color. Wow. Yeah, I went all out. Usual office hours for the rest of the week. Today after class, tomorrow at 10, tomorrow at 1. And homework for Friday. We're going to have presentations on the first graph theory packet. Well, there's more than one. And proof portfolio entries if you would like. I think I got everything back to you that all the proof portfolio entries and mistakes journal entries that you'd submitted. So, other than, a little matter of your take-home exam, I think I'm caught up on grade. Question. You want to go for the walk before or after the presentations?
After.
After and before we start graph theory?
Yes.
Okay. That's actually very appropriate because the first page of graph theory is looking at an example where we talk about people going for walks, funny enough. So that actually makes for a great transition. Okay. What do you call a number that can't sit still?
A fidget digit or something.
I like that. Let's go for, though, is a Roman numeral.
Oh, wow.
See, even the joke is about going for a walk almost. It's
meant to be
better.
Yeah, I do. I
To
think
be
it
honest, that was better.
That was on the top of my head.
Ollie's is
Fidget
better.
digit
I
sounds
vote to
funnier.
replace it.
Or
Vote
just
to replace
spell
you.
Fidget, but with
Alrighty,
Okay.
yeah. Okay. Absolutely not. Let's see. Let's go with N. Which means N. Alrighty. Lily, you want to kick things off for us?
yes.
Alright, so I will be doing page 3, in which numbers be defined by f of x is equal to sine of x. So if t is 0 to pi, find f of t, in which we said it would be our numbers from 0 to 1. For the first, I don't know. For the second one, if s is the two numbers, is a set of the two numbers 1 and -1, find the inverse of s. So this is what we said. Since it's all real numbers, it'll be x such that it's pi over 2. I don't know if this is the correct notation. Plus pi of x. And this is just because this repeats cyclically. So at every pi over 2, 3 pi over 2, 5 pi over 2, it's going to be 1 or -1. Yes.
Does an x need to then be defined as an odd number? Or, oh, I see how you're taking care of that, never mind.
And then, yes.
Sorry.
Yes.
Couldn't you end up with pi plus pi over 2, which is 9? Now I'm confused by your notation, actually.
Okay.
If you made x an element of the integers instead of the real numbers, would that provide?
Oh, wait, yeah. You're right. I think that would, because it'd be 0, 1, 2. Yes, because you're just adding, thank you. Because you're just adding one whole. I actually had that written down. I don't know why I second guessed myself last night. But yeah, you're just adding pi every time, just one pi. because it'd go from pi over 2 to 3 pi over 2 to 5 pi over 2 to 7 pi over 2, because that's where sine of x is going to equal 1 and then negative 1. And then the last one is to find
Actually, before we move on,
yes.
can you do me a favor, Lily?
Yes.
Can you swap the order of x and z in the pi over 2 plus pi x? Because right now it looks like you're saying the set is the set of all integers such that pi over 2 plus pi x something. Whereas typically you start with the things that you want to include, which is
Pi over 2 plus pi x,
and then maybe
where
like,
x is in.
I like it, yeah, because then I think, I mean, the set of everything that looks like that is of the form pi over 2 plus pi times x, where x is allowed to be any integer. I think it's a little bit more
Makes more sense.
precise
Thank you.
notation.
Yes, thank you. We always want to be precise in here. And then find a set K in R such that F, the inverse of K, is the null set, and then I just said, I didn't write it in set notation, I could, but I just said where K is greater than or equal to 1, where K is a real number. And this is because the sine function is only defined from -1 to 1. So anything greater than that, there would be no connection back to the sine function. Yes.
Wouldn't it be k greater than 1 then? 'Cause
Oh, sorry, yeah, greater than 1. That's what I meant.
So how would you write that as like a set?
I think just about that way. Set K, well, is such that x is a real number. So basically just this way.
Maybe you could also use interval notation to write like the open interval from 1 to infinity. Would be kind of a nice, maybe a simpler way of writing it out without having to use special set notation. Cool. Any other questions for Lily?
If you're going to write it in that, like sort of the first form, could it be like the absolute value of x is greater than 1?
Yeah. Because anything less than -1 would also fall in this range. Yeah.
That would be sort of a
Complete.
maximal set, maximal example of k, and that any other k you can think of for the third one will be a subset of that one. All right, nice job, Lily. All right, next up, we're going to prove some properties about the image of a function.
So, for this problem, the idea is we've got a function, and for every number index, suppose that t is a subset of A, so that we're essentially mapping things from subsets T to some group in B. Alrighty, so I'm doing part A, where the function of the union of all these sets is equal to the union of the function of all these sets, if that's kind of how I wrote that. Or like f of all inputs equals like all the outputs. So I started with let x exist in union of f of t sub k. So yeah. Okay, I guess I'm doing this backwards. I'm doing the second part first. Is that okay with everyone? Okay, sweet. That means that x exists in the function, the result of the function, so the codomain of f of t sub k for some one in this case. Right, just x just has to exist as a result of one of the values in this set. Then for there exists some x naught in t sub k such that f of x naught equals x. Then because x naught is in t sub k, x naught is in this union here. And let's see, I'll show you real quick. So x exists in let's see, I don't want this. I want in doing the second part. I'm just thinking this backwards. In the function of t sub k. So we have now, therefore, t sub k is a subset of function of the union of t sub k. Does that look good so far? Alright, move on to the actual first part of the proof, if we're going kind of from left to right.
In general, when you're proving two sets or subsets of each other, it doesn't matter which one you really do first.
Okay.
As long as you do them both.
Alright, so now we'll let x be part of the other side of the equation, which is then let's see here, x is in the domain and there exists an x naught in t k where to n because x naught is in t sub k. X exists in the function of t sub k. Does that make sense? I'll keep going with it. And thus exists therefore is a subset of or k equals 1. You say k. I think that's it. So here we've proven that they are subsets of each other. Any questions? Yeah.
So, you're able to say that X naught exists in T of K because it's dealing with the union and, like, if this were the intersection, you'd have to come up with like a different approach. Is that correct?
Yeah, so that's why I signed up for this one instead of the intersection, because I would have a little bit more concern with that. But yeah, just for some, let's see here. Yeah. This all looks like gibberish now. Yeah, I guess if anyone else has an answer, go for it, because it's taken a long time for my wheels to turn. But
I'm sorry, what was your question, Olivia?
So since we're dealing with the union, we're able to say that X naught exists in T of K. But if we were dealing with the intersection, we wouldn't be able to like have that as part of our proof.
Like, we need X not to exist in like every T sub K instead of just a single one. I think would end up happening. Any other questions?
I guess, yeah, it'd be for every instead of some. Is that kind of what we're looking at?
So I guess I'm a little confused why you need to use, like, I follow the logic, but why you need to use X naught, because can you not, so you say like X is an element of f of T sub K for some K, right? So can you not then like just immediately conclude that it's in the union of all of f of T sub K? Or sorry, that it's in.
Are you looking
Actually, now I'm just confusing myself.
I would say, are you looking at the first part?
Yeah. Well, for both of them.
So you're saying that X naught is not necessary,
Well, I don't know.
or you're asking?
Yeah.
I think it's helpful to have personally.
Yeah.
Just kind of make it very clear like where each of the different pieces lie, so in order to look at it. If it's strictly necessary, you can probably find some way of getting by without it, but I'm glad that Laura included it here.
Yeah.
In the second part of your proof, Laura, what relationship does X not have to X?
Wait, this one here?
Yes. Say like there exists an X naught in T sub K. Like,
Oh, yeah, there's this also X naught in T sub K. Such that, oh my goodness. Let's see here. Yeah, such that function of X of naught equals X.
gotcha. So you're the fact that X is in the F of the image of the union means there's something in the image of the union, or there's something in the union that gets mapped to X.
Mm-hmm.
Gotcha. Cool. Any other questions for Laura? All right, thank you, Laura. Alrighty, and last up, Adam's gonna tell us something about the intersection. Thank you.
We're basically looking at something very similar, except we're only going one way, which makes it a little bit easier, and then we're considering the intersection. So we're looking at f of the intersection of the t sub k's is a subset, is a subset of the intersection of the function of t. Okay, great. So I said let's start with some element y. So let y be an element in f of the intersection of k's such that y is the image of exactly one element x, which is an element of a, is the image of exactly one element of a, call it x, under f. So basically we can write y equals f of x for exactly one x in a. Okay, great. And since y is in this set, we can conclude that x must be an element in the intersection of all these subsets of A. Then, and then we can write, which implies that x is an element. I'm going to write this a little differently. I'm going to write for every I, x is an element of t sub I. Right? Because if it's in the intersection of all of these, or I guess I could use k, does it really matter if I use I here, or should I switch it to k's? Would that be more proper? I guess I just kind of default to i's.
Honestly, it's fine.
Okay.
As long as you're consistent about it, like you're switching from calling them like all of the t sub k's to in each individual t sub I. It's a little unorthodox to change up the variable like that, but it's fine.
I can just write k, that's not a big deal. I think I just did that absent-mindedly. So basically we're saying just for every k, x has got to be in that subset, right? And that's just the nature, that's just the consequence of it being in the intersection here. Well then, if we evaluate, if we transform all of the elements of every t sub k under f, this is going to imply that y is going to be an element of f of t sub k for every k. Same thing. I should actually write that out just to be explicit, because otherwise it's sloppy. Then, for every k, y must be an element f of t sub k, right? Because we know when we transform x under f, it's going to produce y. So that's just another consequence of y being, or x being in all of these subsets. Well then, the definition of this just says that y is an element in the intersection of all of these t sub k's. And thus, we've proved that f of the intersection of the t sub k's is a subset of the intersection function of the individual sub k's. Anyone have any questions?
So on your first line, you have like the y is equal to f of x for exactly one x. So
This line?
yeah, so does this theorem only hold if the function is one-to-one? Or like, could it, like, would it also hold if it like wasn't one-to-one?
Well, I'm not necessarily saying it's one. Well, I guess no, because it's an arbitrary element, so would that imply that it must be 1-to-1? I think for the intersection it might have to. Because if y is the element of, let's say, two elements, x and z. Let's say x is in some of these t sub k's and then z is in all the others. Then y would be, where would y be? Then y would actually be here, wouldn't it? Because if you took the intersection, all of those, x and z wouldn't be in them, because if you took this right here, x and z would not be in that, because they're not in all subsets. So then we transform that under f, y would probably not be in there if the only two elements from those subsets get transformed to y is x and z. So I guess for this to hold, I think so, I think that's a good point. I guess I just thought about it this way because I'm like, it'll be convenient, so that's why I wrote it that way.
What if you have that there's both an X and a Z that are distinct, that both happen to be in all of the T sub Ks,
Oh, well, that would then, yeah, that would work then, wouldn't it?
without necessarily being one-to-one?
Yeah, so it wouldn't have to be one-to-one, it just has to be some element that gets transformed into why it has to be present in all of the subsets, though there could be multiple that get transformed in the same format.
Yeah, I don't think we necessarily need that y equals f of x for exactly one element in A, but there could be multiple elements in A. It just so happens that at least one of those elements has to be in the intersection of all the T sub Ks.
Yeah, I mean, when I wrote it, I was like, this seems convenient, so I'm going to use it, so I just want
But did the theorem say that the function had to be one for this to work?
No, I just thought it might be convenient.
One-to-one is a nice property to have, but it still proves something. Some proofs don't necessarily need it. Good question, Isabel. Any other questions for Adam? Alrighty, nice job. Yeah, good job, everybody. Some, especially Adam and Laura, those are some tricky arguments to make. Okay. Raise your hand if you've gone on a walk in the last 2 days. Okay, let's do.
I had to think for a second.
Lily, the face you gave me, it's like, what a ridiculous question. This is what that looked like. Okay, let's see. Let's have groups for today. Don't worry, I remember we're going to go for a walk. Keep your hands up. I'm dividing up the groups so we can have a group activity on our walk.
Oh.
Helen, Mariah, Adam, Holly as a group. We'll do Griffin, Lily, Jacob as a group. All right, couch potatoes. If you're not in a group yet, raise your hand. Say as I say, as I look at like the two athletes here in the front row. Let's see. You know what? Let's do Sophie, Madeline, Alex as a group. And then what does that make? Laura, Isabel, Laurie, Olivia? Okay, get in your groups, and then I'll give you your assignment for the walk today.
I was like, I don't think I'm going
Dr. Gerstle, did we distract you while you were teaching your geometry class this morning? We were throwing the golf ball around outside.
I was confused, a little bit. I was confused. I was like, I saw that like there was some commotion happening outside. I didn't
Yeah.
look away long enough to see what exactly you were doing.
Carl wanted to throw it as hard as he could at like Strosacker and bounce it off, but then we figured out that we might dome somebody if they walked.
I was gonna say that sounds like a terrible idea.
Yeah, that was Carl's idea, it wasn't mine.
That sounds like a terrible idea, Carl. Anyways, here's your assignment for your walk. While we're doing a lap around this building, you need to figure out with your group members where each group member's favorite place is in Hillsdale to go for a walk.
Oh.
Easy.
All right, off we go.
Alright. Does anyone have a favorite place? Does anyone know off the top of their
I don't
head?
know.
It's like a really nice walking trail. That's it's like. Oh, I know exactly. Oh yeah.
what happened? Who splintered off?
So we're slower than others.
Thank goodness. Already walking way slower than I feel comfortable.
I'm surprised they didn't have you like roam with like another.
Sit with your groups.
Well, there is only one other, and she is from like Adrian. So she knew somebody that was gonna be here.
Okay.
Oh yeah, yeah. I remember that. She went to like the end of it.
So, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yay, we didn't lose anyone.
Oh, you definitely said that. Ooh, fancy. I wrote here for a second.
Take that and pass it back. So passing out by column because nobody else got in their groups.
I guess you better than
Alrighty. So, now that you both feel refreshed, we've gone for a walk. We're going to talk about a famous location to try and go for a walk in the 1700s, which is the city of Königsberg, which I kind of gave you an image of. So Königsberg's been famous for kind of being separated into 4 separate land masses, with the bridges, with 7 bridges connecting them. And there's a long-standing question for a long time of, does there exist a path or a walk that you can go on that goes across each bridge exactly once?
Can you start from anywhere?
You can start from anywhere, but the only way to get from one landmass to another is by bridge. No swimming allowed. No lifeguard on duty. 1700s. So the only way to get from one landmass to another is to take a bridge. Does there exist a way to go from does there exist a way to traverse all 7 bridges without ever having to go back and do one a second time? And this question was solved by Leonhard Euler in 1736. What?
Euler just takes everything, you know? Takes all the fun out of everything.
Well, not necessarily. There's also Gauss. My calc class this morning, it was Gauss for everything. There's also David Hilbert, my geometry class. Every class has its party pooper mathematician who steals all the results for themselves. But solved by Euler in 1736, and basically graph theory was born from that, from looking at this problem. So, something for you all to think about is, and I'm not going to tell you if the answer is yes or no right now, can you find a path in your groups, and also go through the rest of this packet? You have your groups, you have your packet, have fun. For the first page, if you're having trouble finding a path, you don't have to like prove that there does not exist a path quite yet. That maybe comes later. But if you can't find a path, what order does you cross the bridges in?
Because you end up stuck on it. You have to cross without.
Yeah.
I don't know if there's one. Yeah, let's see what I got.
No, considering it's so long. I think maybe we
Oh.
started here and then like this. Or like if you go on like different here to here. There's a really big hint because
There's like 2 other bridges.
why
So
would
these
you
are not
use
like 7, and then you'd have to
I'm
go
not sure.
each 4 or something. Like, start.
Which is I don't know.
Interesting idea.
You got it?
come back.
I've tried to
How long it was?
Yeah, you can start and end anywhere you want, as long as it satisfies the condition that you crossed each bridge exactly
I
once.
think 3 is the problem.
How you on? Everybody going? Welcome. Then the pair G, B, coming here. Holy graph is set.
Yeah, true.
Guys,
with like, I mean, there's like 3 elements.
7 bridges.
That's fancy.
It'll be
Although a lot of them will be pretty useless.
like an ordered pair.
You know, like from 5 to 4 or
Is that what that
something.
means?
Say what?
I mean, like a BBS set, so there's like a bunch of elements or whatever,
That we'll call our vertices.
and then be an unordered pair.
So I'll give you an example at like the bottom here. So when I say a graph is a combination of V and E, that just means the graph has vertices, the graph has edges, where edges are just sets of 2
So, like,
vertices.
A graph of that would be like a,
I can't figure it out either.
Well, I would say the graph consists of all of this, like all these, this set V and this set E together create a graph.
I know.
You could have another graph where you have 3 vertices, A, B, and C, and maybe 1 edge connecting B and C, and that's it. That would give us a different graph. If you turn the page, there's a pictorial example of the graph that might help you out.
Oh, that's what I was trying to do.
That wouldn't even be in there. So just out of there.
Like the G is, how is like G a pair if
So G is just basically, think of G, a graph, as being a set of 2 different sets. You've got, with a graph, you always have your set of vertices, which are just the single things in the first graph, the V. And then you also have another set, which is your set of edges, which is, where an edge is just gonna be a set consisting of 2 vertices.
Back at cities.
Try turning the page if you want like a pictorial example. Maybe.
So I don't know if this is the right way of thinking this, but I think of like 1 and 2 as like closed loops and 5 and 6 as like closed loops, leaving 3, 7, and 4, but you can't get a direct path to any of them. Like you can't get closed loops to any of them. What do you say?
That's an interesting idea.
I don't know where K is.
or what?
They probably
Do you think
Dubuque, Iowa.
like
Boom!
Wow.
do you eventually like just adding 2 more bridges like what
Actually didn't know that. That's
eventually
really
you're
cool.
gonna have to go up one and not the other, which is like a closed loop. So taking out these 2 and these 2, you're left with like
Yeah.
this.
In my I lived my 5 years in Iowa, which is why if you could ever go into Iowa, knows that's why.
Iowa's the best state.
Not enough.
You told me that when we were freshmen. I was like,
Pretty good state.
what a
I don't know
weirdo.
if that's it.
Why?
It's an objective fact.
I would not go that far.
I don't think this is really conclusive proof, but
Yeah.
it.
What's your definition of best?
I mean, if Iowa were to be wiped off, everyone would notice.
That's true for every state.
Okay, that's me.
No.
Depends on the manner in which it was wiped off. If like it was wiped off and our memories of it were wiped out as well.
Would we actually feel lack?
Maybe not.
Okay.
You would feel lack.
Any questions? Okay.
I might just take it.
So it's not like when you say graph.
It's in
Yeah.
your V, it's not very
It's not necessarily.
'Cause
text line.
The E is just the same.
Yeah, it's not like you have a vertex as your X
Would
and
we worry
an
about
edge as your Y coordinate. The graph is just kind of 2
no
different
direct way to
sets.
get to
You
it.
have your set of vertices, your set of edges, where the edges have to be pairs, sets containing pairs of vertices.
It's Green City.
But you wouldn't write it out in the XY form like you would for like a graph, the way you're used to thinking about it.
I just went to Pittsburgh this summer, maybe for the first time ever, and it's really kind of cool city.
That's a question, not a.
Oh, have I been?
Yeah.
No, but I did see all the high stuff like everywhere, and I was like, interesting.
For the city's example with the edges, feel free to abbreviate some of those edges.
This
Or you could go full Griffin mode and write them all up. Although, I don't know what this NY is. I don't see an NY in this.
Yeah, exactly.
It's,
Hypocrite.
Is there any city I'd be worried about?
I'm worried about the city stuff.
Fair. Looking at this graph of a transportation network, are there any cities that worry you for reasons that you could see in this graph? Are there any cities that might have a hard time getting stuff transported to or from?
Do they all begin with a different letter at least?
This is just random cities that.
okay, did you have
Oh, okay. I think I used the first like
Oh,
8
8.
letters.
Rochester?
Yeah.
I didn't do Rochester, but. Philadelphia.
It's B2, B2.
I only have 7 total signatures.
This B2, B3, B4.
I was proud of this graph.
Oh, yeah, I don't have
Spent a
much.
while trying to make it vaguely look like the configuration they would be on a map.
Yeah, it makes,
Yeah.
it makes sense for that.
Yeah.
Yeah, I guess what counts.
It's just, it wouldn't be in the edges. Okay.
Would anybody like me to send them, by the way, the tech code for this packet, just so you have something they can use to make graphs? Because making graphs in tech is not always the easiest thing to do. Okay, Adam, email me after class and I'll send it out.
Okay.
Yeah, for real.
So it's like the number of,
I haven't even thought of it, you know, like.
so like, is
Number
this,
of edges,
is
so
this
like
the
go back and
degree
rewrite
three?
everything, just, yeah.
I literally do that sometimes.
And vertex is just degree 1.
Or just wrap it around the side of the page. It's called a triangle if X divided Y and Y divided Z.
Like V4 is V2, V2 is V3, and V3 is
Sounds like a triangle. You could also define things like quadrilaterals and pentagons, etc. on a graph, but those
Yeah. I know,
definitions are a bit
there's
messier.
in Philadelphia.
Yes.
Yeah, that's what I'm trying to do too. I know, messing with my whole mind.
How embarrassing.
I know, isn't it? I should be ashamed.
I was like, okay, how do we know how many sets we have for edges? But it's super simple. Okay.
Crazy how that happens.
Number of edges determines your number of edges.
Okay. Yes. bottom question is kind of vague, like, is there any city that would be worried about for any
Maybe should I use some like really emotional like reason? Crime rates in Chicago.
Yeah.
Oh gosh, I was just,
New York.
just this morning I was reading a Facebook post by a friend of mine who went to University of Chicago talking about like all the crime that was there.
Yeah, that's what I want to talk about and why I'm worried. It's not to be anything mathematical, it's just the
I mean, it's definitely just.
No, we shouldn't be worried about you.
I need to word my
Fact that
question.
there's nothing that could teach you.
No.
Not a problem.
They're living the
Yeah.
Oh, so
It's a very frequent occurrence in class that after listening and after conversations, I realized I needed to
Oh my
word this
gosh.
carefully.
I was like about the pollution in New York. It's gonna be like
Oh,
really
the
bad.
rat.
Yeah.
Oh,
It's true.
Subway's so terrible. Yeah. Let me start writing.
In Philadelphia, that bell in the hall with a
Boston.
crack in it, that's a
Oh,
problem.
Boston, has anyone ever heard of the Boston Tea Party? That's very funny.
Just Toledo.
I mean, Cincinnati is just like,
Most
like scary.
Yeah, like,
Wow.
I'd rather be in
A lot
Toledo.
of-
There's like.
Last year's really
No one likes cheeseburgers.
I'm gonna be
Okay,
completely honest, I have no idea.
I mean,
I just saw something
really
about
high
that.
body. Oh, is that where it's at?
But I don't know, it's just,
That's
Every edge is gonna have two.
There's lots of.
Oh, you look like you had something you wanted to say.
No, I didn't.
I was discussing why the cities with the most
Every
edges
degree.
don't contribute to it.
So think about
Oh, yeah?
it,
Yeah,
if you
because more
want
connected cities tend to have a higher probability of like high
me to use
So,
Well,
because
yes,
they
this
can
is-
get
there's
in and out
only one
easily.
edge,
This is true.
there's gonna be, this is degree one, this is
Sadly true.
so the total degree.
Okay, we are about out of time for today.
Start this.
So,
I understand what we're trying to.
just so you all know, what we're going to be doing in graph theory, because graph theory could be an entire semester course by itself, honestly. There's so much you can do with like edges and vertices and such. What we're going to be building towards in this class, though, is trying to be able to answer the question of, does there exist a solution to the bridges of Königsberg? And in general, given any graph, does there exist a path that takes each edge exactly once? That's kind of where we're going to be building. That's kind of like a big motivating question that we're going to be building towards and proving some other results along the way. So with that, hope you all have a good rest of your day. I will see you all on Friday.
There's no connection.
Yeah, that's what I, like, that's the basic case.
I wrote the assumption.
Yeah, that, because I had written that and I was like, wait a minute.